these rolling chairs? Will it be like a week or so for our tests to be graded and all?
I have everyone's. I would say within the next couple of days.
Okay.
Yeah, I tried to print them off over the weekend, and the printer ran out of toner. So, anyway, yeah, within the next couple of days, I have. I checked off. Everyone has turned theirs in.
Why are we meeting here then?
A couple of reasons. One is the remote control on the other camera, it sticks. Sometimes I can't get it to zoom or pan. This one works a lot better. Also the when it shows me on the window, it's a really small window. I need to see the window to make sure that I'm not off screen when but there's several advantages. Okay,
Then we'll listen to him. Why? How good?
Okay, I'm going to wait just a couple more minutes to see if anyone else joins. Oh, there's another one. Okay. Okay, I'm going to go ahead and get started. I'm going to share my screen. Okay, this week's lab is called isomerism. My plan is to do it entirely remotely online. It is a model making exercise, but I think that it would be better if we weren't in close contact and handling the models and so on. So this week's lab, I'll send you instructions out for that, but that'll be entirely remote. Okay, so I'm going to share my screen. And, okay, here we go. Okay, those of you on Zoom, can you hear me? Can you see the screen?
Yes.
Okay, thanks. Okay, we're going to start a new topic today. This is in chapter 4 of your textbook. It is the study of chemical reactions. This opening photograph, this shows the ozone hole over Antarctica. That's an example of where studying kinetics is important. Okay, we're going to study both kinetics and mechanism. Mostly mechanism in this chapter. Okay, an overall reaction involves going from reactants to products. We'll review thermodynamics, which is the study of the energy changes that accompany chemical and physical transformations. We'll review a little bit about kinetics. And we'll talk about the idea of a mechanism and using arrow pushing to show the movement of electrons, which may be something new. But a mechanism is a step-by-step description of how the reaction happens. The mechanism describes the sequence of steps. It shows which bonds are formed, which bonds are broken, and in which order. Okay, a mechanism is not necessarily something that can be proven, but if it's, it can be judged reasonable if it corresponds to the available evidence. Okay, we're going to start with a very atypical reaction. Most of the reactions, 90-some%, that we'll be looking at in this course involve asymmetric breaking of bonds. In other words, you have a shared pair of electrons, and when the bond breaks, both electrons go to one side or the other. This is an example of a symmetric breaking of a bond, what we call homolytic. Okay, when you react methane with chlorine, okay, in the dark at room temperature, nothing happens. But if you shine blue or ultraviolet light on the reaction mixture, you have a substitution that takes place. One of the chlorines replaces a hydrogen on methane, and the two products are chloromethane and hydrogen chloride gas. Many molecules of product are formed from the absorption of only one photon of light. So this is a chain reaction. This particular reaction involves what we call free radicals. And again, we're going to look at very few free radical reactions in this class. Most of them will involve ionic intermediates. But in this particular reaction between chlorine and methane, there's 3 steps. Okay, there is initiation, there's propagation, and then there's termination. Okay, and in initiation, what happens is you generate a radical intermediate. Okay, what's a radical intermediate? A radical intermediate is a species. It is an atom or molecule that has an odd electron, an unpaired electron. Okay, so the first step generates the radical intermediate. Propagation involves taking that intermediate, it reacts with a stable molecule to produce another reactive intermediate and a product molecule. Okay, so in this case, a free radical generates a free radical, and that generates another free radical, and then the process keeps going. It doesn't go on forever. There is a termination step, and these are side reactions that will destroy the reactive intermediate. All right, so here is the first step, the initiation. Okay, so we have a chlorine molecule. And if we hit it with blue or ultraviolet light, this gets absorbed by the chlorine molecule, and the chlorine molecule splits symmetrically, or we say homolytically. These arrows have a single barbed head, or like a fish hook. Okay, that indicates the movement of one electron, okay, rather than a pair of electrons. Okay, we use an arrow with 2 barbs on the head to show movement of a pair of electrons. This is movement of a single electron. Okay, so one electron goes this way, one electron goes this way. And so we split the chlorine molecule into 2 chlorine atoms, which are also free radicals, since they have this odd electron. Okay, these are some other examples of free radicals. Okay, we of course have halogen atoms as intermediates. The hydroxy radical, this is an important intermediate in atmospheric science. It is also it's also an important intermediate in hydrogen peroxide or peroxide oxidations. Okay, this is a methyl radical. Here's an ethyl radical. Okay, so free radicals are reactive species with odd numbers of electrons. Okay, the halogens have 7 valence electrons, so one of them will be unpaired. Oftentimes you refer to the halogen atoms as atoms rather than radicals, but they are radicals. Okay, so that's the initiation, okay, where we split a molecule into 2 atoms. Okay, there's several propagation steps. This is one of them. Well, molecular chlorine is pretty reactive. Chlorine atoms are even more reactive. Methane and most alkanes are not very reactive, so this tells you that of course the chlorine atom is a very reactive species. Okay, so let's take a look at what happens here. All right, this CH bond, okay, we have a pair of electrons, splits up. One of the electrons joins with the chlorine to form HCl. The other one is left behind on the carbon. Okay, so we're propagating another free radical. Okay, here's another possible propagation step. Okay, that methyl free radical can react with a chlorine atom, chlorine molecule, which was not split, and this generates another chlorine atom, and also generates a product molecule, chloromethane. Okay, so here's a propagation step. Here's another propagation step. This is the overall reaction. Okay, and then we also have some termination steps. One of the termination steps involves two of these free radicals combining to form a neutral molecule. In this case, a methyl radical and a chlorine atom. Okay, that produces a product. And then you have some other termination steps that can take place. Okay, after we split a chlorine molecule, the two chlorine atoms can come back together. We can have two methyl radicals combined. And in fact, we observe ethane showing up in the product mixture. So that's consistent with this mechanism. Okay, and then we have some collisions with the walls of the container, which terminate the reaction. Okay, chemistry 2, you learned about equilibrium constants. Okay, for a general reaction such as this, the equilibrium constant is equal to the products over the reactants. Each species is raised to the exponent, which corresponds to its coefficient. Okay, the coefficients in this particular reaction are all 1. Okay, it's products, chloromethane times HCl over methane times chlorine. And we can see that the equilibrium constant is a very large number. Okay, it's 1.1 times 10 to the 19. So that tells you this goes all the way to product. It goes to completion. Okay, and then for review, free energy, we get the change in free energy from the energy of the products minus the free energy of the reactants. This is defined, delta G is defined as the amount of energy available to do work. A reaction that has a negative delta G is favorable and spontaneous. Okay, so in terms of the equilibrium constant, this is the relationship. Delta G standard is equal to minus RT log K. Or in base 10 logs, it's times a factor of 2.303. R is the gas constant in joules or kilojoules, and T is the temperature in Kelvin. Free energy, okay, determines whether a reaction is spontaneous. If delta G is negative, then it's spontaneous. If it's positive, then it's not. There are actually two factors that go into delta G. There's enthalpy and there's entropy. Okay, and this is the relationship. Delta G equals delta H minus T delta S. All right, so this is a graph that shows the relationship between delta G and conversion to products. Okay, so if delta G is 0, then we would have like 50% conversion to products. Okay, we'd still have a lot of starting material left over. As delta G gets more negative, then we have a greater conversion to products. Okay, so if delta G, for example, is negative 20, we have almost 100% conversion to products. Okay, I haven't done the calculation, but if okay, if KEQ is 10 to the 19th, that tells us that our delta G should be a really large negative number. Okay. All right, so delta G incorporates both enthalpy and entropy. Enthalpy is the heat released or absorbed during a chemical reaction. And if it's a standard enthalpy, it's under standard conditions. If delta H is negative, then heat is released. It's exothermic. If delta H is positive, then it's endothermic, and heat is absorbed from the surroundings. Reactions favor products with the lowest enthalpy, that is the strongest bonds. Okay, back in the early 1800s, it was believed that only exothermic reactions could be spontaneous, but of course we know that that's not true. We can have spontaneous endothermic reactions. We also have to consider entropy. Entropy is a change in randomness, disorder, or freedom of movement. Increasing the heat or the volume or the number of particles will increase the entropy. Spontaneous reactions will maximize disorder and minimize enthalpy. A lot of the times the entropy term is small, not always. Usually the delta H term will dominate, but there are situations where, in fact, there's a large increase in entropy for an endothermic reaction and it's spontaneous. Okay, so here's the calculation for our chlorination of methane. Okay, using this equation. Okay, we know what K is. And if we calculate delta G, it is negative 108.7 kJs per mole. Okay, so this, since this is such a large negative value, that shows that the chlorination has a large driving force and it pushes toward completion. Okay, next we'll look at bond dissociation energies. Breaking a bond or bond dissociation requires the input of energy. It has a positive value. Bond formation releases energy. And we can estimate delta G for reactions using bond dissociation energy values. Especially for something like what we just looked at, where everything is in the gas phase. If it's in the solution phase, it's going to be more complicated. But we can estimate using these bond dissociation energies. We have different values for bond dissociation energies depending on whether the bond breaks homolytically or heterolytically. Okay, in this example, it broke homolytically. Heterolytically, again, is where it breaks unsymmetrically, where the most electronegative atom gets both electrons. Okay, so here are some bond dissociation energies. Okay, so to break a chlorine-chlorine bond, okay, that is positive 242 kilojoules per mole. Okay, to break this particular carbon-chlorine bond heterolytically, okay, that will vary with solvent. Okay, remember, breaking a bond will be a positive delta H. Forming a bond will be a negative. Okay, that releases energy. Okay, so here's a listing of the bond association energies for this particular reaction. Okay, so we list the bonds broken. Okay, we're breaking a chlorine-chlorine bond, and we're also breaking a carbon-hydrogen bond. If we broke more than one of each type of bond, then we would need to multiply by that factor. But in this case, it's just one bond. Then we're forming two bonds. We're forming this HCl bond, and we're forming a carbon-chlorine bond. Okay, so if we total up these bond association energies, these are homolytic. This is per mole. Okay, we get 679 kJs from the bonds broken, and then we get negative 782 kJs for the bonds that are formed. And the sum of those is negative 103 kJs per mole. So this is an exothermic reaction. Okay, in terms of entropy, that might be a little more difficult to estimate. We could use the equation delta G equals delta H minus T delta S. We do have the same number of product and reactant gas molecules, so just looking at the reaction, it would be difficult to estimate whether the entropy would be change in entropy would be positive or negative. Okay, so that's using bond association energies. Okay, in some of our mechanisms, we'll be talking about kinetics. If a reaction follows an experimental kinetic rate law, that tells us whether a mechanism is reasonable or not. Kinetics, of course, is the study of reaction rates. The rate of the reaction is a measure of how the concentration of products increases while the concentration of starting materials decreases. Okay, a rate equation or rate law is the relationship between the concentrations of the reactions and the observed reaction rate. Okay, rate laws must be determined experimentally. Okay, this may be a little difficult to read, but these are bond association energies in kilojoules and kilocalories.
What table number is that?
4.2. Okay, I just want to point out some things here. Okay, the carbon-fluorine bond is especially strong. The OH bond in water is especially strong. Okay, this is, see if I can find it here. Okay, CH bonds. This will be important, actually 2 chapters ahead. Different CH bonds actually have different bond energies. Okay, depending on whether the H is on a alkyne or alkene or benzene ring or alkane. Okay, so here's a very general rate law for the reaction of A plus B. Okay, the rate is equal to some rate constant times A raised to a certain power and B raised to a certain power. These exponents A and B have to be determined experimentally. K is also determined experimentally. The sum of A plus the sum of small a plus b is the overall order. Okay, order is the number of molecules of that reactant which is present in the rate determining step. Okay, so if there's more than one step in the reaction, it's going to be the rate determining step. And if we have several steps, the rate determining step is the slowest step. Okay, here's a review of the Arrhenius equation and activation energy. Okay, the rate constant depends on the conditions of the reaction, especially the temperature. Okay, and you can see that there's an exponential relationship here. A is what's called the frequency factor. EA is the activation energy, usually expressed in kilojoules per mole. R is the gas constant. T is the temperature in Kelvin. Definition of activation energy is the minimum kinetic energy needed to react. Okay, so here we have some hypothetical reaction at 300 Kelvin and 373 Kelvin. The y-axis is the fraction molecules having a certain energy. And this dashed line is the, these represent different activation energies, these dashed lines. And in all three cases, at the higher temperature, we have a greater fraction of molecules that exceed that activation energy at higher temperature. Okay, so here's a one-step exothermic reaction. Okay, we have the energy of the reactants. And going from that level up to the maximum here, that difference in energy is the activation energy. The smaller the activation energy, the faster the rate. This is exothermic because the energy of the products is lower than that of the reactants. And so the difference between the reactants and products is delta H. And in this example, that would be, delta H would be negative. Okay, up at the top of the hill is the transition state. And transition state has a very short existence. Okay, it may be picoseconds or femtoseconds, 10 to the minus 12, 10 to the minus 15 seconds. Very difficult to observe. Okay, so the highest points are the transition states. Okay, there may be more than one. In the previous example, there was just one. The lowest points between products and reactants, between reactants and products, are intermediates. This particular reaction did not have an intermediate. It just went from reactants to products. The reaction step with the highest activation energy will be the slowest step and will be the rate determining step. Okay, so a reactive intermediate is a species that's formed in one step, but then it's consumed in a subsequent step. So it doesn't show up in the products. Okay, so here is two of the steps involved in the chlorination of methane. Okay, so the reactants here are methane and chlorine free radicals. Okay, that first step is endothermic. It is endothermic by 7 kcals per mole, or kJs. This is the intermediate right here, this local minimum. And then there's a second activation energy, a second transition state. And the second step here is exothermic. It's highly exothermic by 110 kJs per mole. Okay, so overall, this is an exothermic process by negative 105. All right, so activation energy, let me start back here. Energy of the reactants, this is the first activation energy. This is also the rate determining step because it's the highest activation energy compared to this one. This is an intermediate. This is the second transition state. And then this is the energy of the products. Okay, so we've looked at chlorine. What about other halogens? Okay, here we have data at 2 different temperatures. 27 Celsius, which is, that would be 300 Kelvin, okay, about room temperature. And then we have 500 Kelvin. Okay, the reaction with fluorine, we can see that that's about, okay, looking at the next to the last column here. Okay, 140,000 versus 1,300. Okay, so at room temperature, fluorine reacts about 100 times faster than chlorine. Okay, also, we can see that chlorine reacts a little more than 10 times faster at the higher temperature. Fluorine reacts about a little more than twice as fast. Okay, so all of these reaction rates increase as we raise the temperature. Okay, so these are relative rates. Something I might also mention for fluorine, okay, with chlorine, we had to irradiate it with ultraviolet or blue light. Fluorine is so reactive that you actually don't even need the ultraviolet light. You can do it in the dark. Okay, going down the column, if we look at bromine, bromine is a lot slower at room temperature. In fact, it's you hardly see it react at all at room temperature. There is, at 227 Celsius, there is a noticeable reaction. So it is practical to do it at a higher temperature. Iodine is just too slow. You can't do the substitution reaction by this process. Okay, it's 10 to the minus 19th at room temperature, 10 to the minus 9th at 227. Okay, we can see the differences in activation energy. Okay, fluorine has a relatively low activation energy, whereas iodine has a much higher activation energy. Okay, so some of the conclusions here from this previous slide. Okay, with increasing activation energy, the rate decreases. Okay, that makes sense. With increasing temperature, the rate increases. Okay, and we definitely saw that. in all of the reactions, the rate increases. Fluorine actually reacts explosively. It's even more reactive than oxygen. Chlorine reacts at a moderate rate. Bromine is too slow at room temperature, but must be heated in order to react. Iodine does not react detectably. I did a little bit of work with fluorine gas when I was in graduate school, and it's so reactive. It reacts with just about anything. It's hard to contain it in anything. I mean, it attacks glass and it attacks all different materials. Okay, so here's the solved problem. Consider this reaction between methane and a chlorine free radical. This one step. The reaction has an activation energy of 17 kJs per mole. And by the way, activation energies are always going to be positive. Okay, they might be close to zero, but they won't be negative. Okay, so draw an energy diagram for this reaction. Okay, this diagram actually doesn't fit because this isn't methane. So we're going to move on to the next slide here. This diagram actually fits the next slide here. Okay, this is an important concept, especially when we start to talk about different functional groups. It's important that you recognize primary, secondary, tertiary hydrogens and carbons. The other class would be a methyl. But primary hydrogens are on a primary carbon. Primary carbon is directly bonded to one other carbon. The secondary carbon is bonded to two other carbons. And the hydrogens on that secondary carbon are called secondary hydrogens. And if that carbon is bonded directly to three other carbons, then it's a tertiary carbon and it's bonded to a tertiary hydrogen. Okay. With methane, we had 4 equivalent hydrogens. So there's only one monosubstituted product. That was the chloromethane. But with propane, we can get 2 isomers for the monosubstituted product. Okay, we can get chlorine substitution on the first carbon. We could also get it on the second carbon. Okay, so it's possible to get 2 monosubstituted products. Okay, well, it turns out that the product yield is not what we would expect if this were a pure random process. Okay, we have 6 of these methyl hydrogens on carbons 1 and 3. We have 2 of these. And if this were a pure statistical process, the ratio should be 6 to 2 or 3 to 1. Okay, but it's not. Okay, it turns out that the secondary hydrogens are actually more reactive. And this calculation shows that secondary hydrogens are 4.5 times as reactive, more reactive than the primary. And so we get about 40% of the primary and 60% of the secondary, even though there's fewer secondary hydrogens. But the secondary hydrogens are more reactive, they react faster. Okay, and that's what this diagram shows. Okay, to form the secondary free radical in the propagation step, that has a lower activation energy than forming the primary free radical. Okay, primary free radical, okay, this carbon with the unpaired electron is directly bonded to just one other carbon. So there's a 10 kilojoule difference in energies between these. And there is a 4 kilojoule difference in activation energies. Okay, so the secondary free radical is more stable and it's formed faster. And so we get more of the secondary product. Okay, so after we split a chlorine molecule into 2 chlorine atoms, okay, the first propagation step could involve removal of a hydrogen off the end to form the primary free radical, or it could involve removing a hydrogen off the middle to form the secondary free radical. And then the second propagation step would be for one of these free radicals to react with a chlorine molecule to form this product molecule and generate another chlorine atom. Okay, the main point of this slide, okay, the previous slide that we saw a little while ago with the bond association energies, that was a little hard to read, but the main point of this is that different CH bonds have different bond association energies. Okay, for a CH bond in methane, that's 439 kJs. For a primary radical, formation of a primary radical, that's 423. Okay, so you can see that the first carbon, the N carbon in propane, has a weaker bond association energy than methane. Okay, for formation of the secondary free radical or bond association for the secondary CH, that's now 413, so that's easier to break. And for a tertiary CH, it's 403, so that's even easier to break. Okay, so all these CH bonds are different depending on their classification. Okay, so here are different classes of free radicals. Okay, this is a tertiary free radical. It is more stable than a secondary free radical, which is more stable than a primary, which is more stable than a methyl radical. Okay, so the more hydrogens we have replaced with carbons, or the more substituted, the more stable that free radical is. Okay, so here's that diagram with chlorine primary and secondary free radicals with propane. Okay, so it's faster and it's more stable to form the secondary free radical. Okay, so secondary CH bonds are 4.5 times more reactive toward chlorination than primary. Tertiary CH bonds are 5.5 times as fast as primary ones. So this shows a calculation. Okay, we have 9 primary hydrogens, but only 1 tertiary. And so if we multiply the number of hydrogens by the reactivity, relative reactivity, we get the relative amount. And we can then use that to calculate the percent yield, predict the percent yield. Okay, so we have about 62% of the primary product and then about 38% of the tertiary. Tertiary CH is much more reactive, but there's only 1 of those compared to 9 of the primaries. Okay, well, it turns out with bromination, bromine is actually much more selective. The difference in reactivity between primary, secondary, and tertiary is much greater. Make sure that I'm on screen here. Find it here. Okay. Okay. So for chlorine, we do it this way. Okay, for chlorine, the relative reactivities are 5.5, 4.5 to 1. Okay, for bromine, those reactivities are 1,600 to 97 to 1. So a tertiary hydrogen is 1,600 times more reactive than a primary hydrogen toward bromination. Okay, so we have about 2 minutes remaining. I'll go ahead and wrap this up in the next couple slides. Okay, so for propane, we get 97% of the secondary and only 3% of the primary, the one bromopropane. Okay, so there's a greater difference in activation energy. We're still forming the same free radicals, so there's still a 10 kilojoule difference, but there's a much greater difference in activation energy. Instead of about 4 kilojoules like we had with chlorine, now it's 9 kilojoules difference in activation energy. Okay, notice also that this step is endothermic. Okay, I'm going to go ahead and stop here. We'll talk about the Hammond postulate next time.